This is Nikesh. Welcome to the presentation of NIOS II 5-stage pipeline processor. I have implemented this project as a part of Advanced Computer Architecture coursework. Let me outline the presentation details. First, I'll be going through objective, NIOS II processor overview, and then proceed with instruction set architecture and implementation of 5-stage pipeline and block diagram and architecture of NIOS II processor will be explained briefly, and finally conclude with the simulation and conclusion. Objective: to realize a 32-bit microprocessor with 5-stage pipelined NIOS II processor. NIOS II processor with pipelined stage is one of the most widely supported of all the available processor. It is a simple, streamlined, highly scalable RISC architecture. The instruction set architecture of NIOS II processor is classified as general purpose register architecture, wherein there are 32 general purpose registers. All the NIOS II instructions are 32-bit long. In addition to the machine instructions that are executed directly by the processor, the NIOS II instruction set includes a number of pseudo instructions that can be used in the assembly language programs. The assembler replaces each pseudo instruction by one or more machine instructions. The design has to be performed using Verilog HDL to compute the dot product of two vectors A and B, and the computation required is shown below by the equation. The design has to be compiled and simulated using Altera Quartus 2 and Synopsys VCS. The 5-stage pipeline of the NIOS II processor has 5 modules: fetch, decode, execute, data memory, write back, and read module. NIOS II processor overview. NIOS II processor issues 32-bit address. There are 5 addressing modes: immediate mode, register mode, displacement mode, register indirect mode, absolute mode. The 16-bit operand is given explicitly in the instruction in immediate mode. The effective address of the operand is the sum of contents of the register and signed 16-bit displacement value in the displacement mode. In the register indirect mode, it is equivalent to displacement mode, where the displacement value is equal to 0. The absolute mode is used to specify 16-bit absolute address of an operand using the displacement mode. There are 3 instruction formats supported by the NIOS II processor. They are R format, J format, and I format. In the project, I have implemented R format and I format instruction set. Instruction set architecture of NIOS II processor. I have implemented R format and I format instruction set architecture, and the instructions present in those formats is shown in the table here. In the R format instructions, you can see the multiply and add instructions with the opcode, corresponding opcode, and the opx values. The upper row indicates the fields wherein the opcode starts from. Since NIOS II processor is a 32-bit processor, and in the I-type instruction set architecture, there are multiple instructions such as add-I, RHI, RI, load, store, BLT, and branch. Their corresponding opcode, source, destination register values, and their index is shown in the above row. Implementation of 5-stage pipeline processor. The block diagram shows the principle of 5-stage pipeline. Here, the NIOS II instruction processor is breaked. It breaks the instruction across multiple clock cycles. This is the basic principle of the 5-stage pipeline. Design a separate stage for the execution performed during each clock cycle. Here, there are 5 stages: fetch, decode, execute, memory access, and write back, which has to be designed separately. Add the pipeline registers to isolate the signal between the different stages. This design gives a basic idea of implementation of 5-stage pipeline. Coming to the block diagram of the NIOS II processor, the block diagram shows the top level module NIOS II processor, and there are sub-modules shown in the figure. The test bench is used to give clock and reset to the main module, and the top module is used to interface with the test bench and sub-modules of the design that are interconnected to execute the NIOS II instruction. The data memory is present in the fetch module, and the instruction memory is present in the fetch module, and the data memory is present in the memory access module. Every instruction is fetched for execution from the instruction memory to perform its respective operation. The architecture of NIOS II processor is shown here. Here, there are 5 stages: fetch, decode, execute, memory access stage, and write back stage. In the fetch stage, instruction memory is used to obtain the instruction every clock cycle, updating the PC counter. The output of in fetch stage is being given to decode stage. Decode stage is used to perform operations such as identifying the source and destination operand, and it generates the control signals to further stages. It also does branching operations. It identifies whether branch has to be taken or not. It is done by this 0 block present here. Once the results of the decode stage is passed to the execute stage is basically a ALU unit wherein it takes the inputs from the decode stage and performs corresponding operations. All the ALU operations such as AND, OR, multiplication, addition, load, and store, address calculation has been done in this stage. Once the ALU result is computed, it is passed to the data memory stage. In the data memory stage, load and store operations are performed if it is an I-type instruction, or the ALU results are bypassed if it is a R-type instruction. The results of the memory access stage is passed to the write back stage. In the write back stage, it outputs the memory access results to the register bank, which is present in the decode stage. This gives a brief explanation on each and every module in the 5-stage pipeline. Coming to the program for dot product of two vectors, which has to be implemented in the project and verified for its functionality. The program for dot product is shown in the figure. Here, there are instructions such as RHI, load, store, add, multiply, and branch. These instructions are fed to the design using the memory instruction memory file, and the test vectors given to the design is n is equal to 6, which determines the loop iteration. A vector values are 5, 3, 6, 9, 8, 12. B vector values are shown here, and the result after computation of dot product is 580, has to be stored at location 100 according to these instruction set given here. Let me go with the simulation. These are my source code files. This is my test bench module. Here I have instantiated the NIOS II processor, and I pass clock and reset signal to the design. This is my instruction memory file. Here the instructions for the dot product program is written and it is initialized to the instruction memory in the reset case. This is my fetch module. Here the program counter is updated and the instruction is fetched from the instruction memory every clock cycle, and it is passed to the decode stage. Decode stage identifies what operation has to be performed. It also determines the source destination operands and generates control signals to the execution unit. This is my execution module. Here, operations such as load, store, branch, addition, RI, RHI operations are performed, and the results are passed to the memory access stage. In the memory access stage module, load and store operations are performed. Initially, the instruction type is identified, such as R-type and I-type. If it is an R-type instruction, ALU results are bypassed. If it is an I-type instruction, memory operations are performed. The outputs of memory access stage is given to the write back module. This is my write back stage. Here, the output of the memory access module is passed to the register bank. Let me run the source code. I use VCS command to run my source code. Once the design is compiled and synthesized, we use /simv to display the results and simulate. I have used $display statements in my design. Here, this shows that there are 6 iterations done, and in each iteration, the operands 5 and 2 are fetched, and the multiplied value is 10. So, and every iteration, the operands are fetched and multiplied, and we can see this MAC result gets updated after every iteration. So once multiplication accumulated is done at the 6th iteration, result 580 is obtained and it is returned back to the memory at 100 location using store operation. These are my waveform results. Here I can see that the results are obtained. We see that here the result 580 is obtained at 103rd clock cycle. Conclusion. Implementation of 32-bit NIOS II processor in Verilog has been done to verify the functionality of the processor. Computing dot product of two vectors. Here, both signed and unsigned multiplication has been performed by the design. Simulation and synthesis of the design has been completed using Synopsys VCS. The processor has been tested with all the instructions: load, store, add I, RI, RHI, branch, and arithmetic instructions such as add, multiply. These instructions are classified under two types, R type and I type. So all the instructions are verified with the processor design. This project gave me an opportunity to learn and explore instruction set of NIOS II processor and enhance my knowledge on various hazards and how to overcome them. Also, stall detection unit implemented in the design, and by using reordering of instructions, the performance of the design has been improved. Future work. To increase the performance of the processor and to reduce the number of stalls, forwarding and bypassing techniques can be implemented. To implement the optimization procedures to achieve good efficiency and performance at a better clock rate by balancing the 5-stage pipeline. To enhance the design, power reduction techniques can be implemented to significantly reduce the power consumed by the design by using various techniques such as clock gating and stall power detection. These are the references used for the project. Thank you.